Hello and welcome to lecture 22 of our comprehensive course on machine learning, data science, and artificial intelligence. Currently, we are doing chapter 19, and originally the name of the chapter was Introduction to Basic Statistics. But as I went on developing chapter, I realized that it is better to introduce several important interrelated concepts in this chapter, and therefore I took some topics from the chapter 20 and 21 also and rearranged them into this chapter, right? So this now is no longer an introduction to basic statistics, but rather it is a comprehensive introduction to statistics, because it is going to be a very long chapter. This is already, I think, 22nd lecture, right? And still I think we will go on for maybe 8 or 9 lectures, right? Now, if you remember, we started the chapter with this descriptive statistics, in which two main topics were the matrix of central tendency and the matrix of dispersion. Then thereafter we did this understanding data distributions, and we did a much detailed discussion on various data distributions like normal and exponential and Poisson distribution and binary distribution and binomial distribution and maybe that Cauchy distribution and so much. Then we are currently discussing this third and the last part, but that is a little bit longer part: central limit theorem and basic inferential statistics. Now, central limit theorem discussion is over currently, and now we are discussing this basic inferential statistic, in which we are discussing this part, hypothesis testing and the p-values. This is just to give you a context that where we are in the entire chapter, right? So hypothesis testing we just started in the previous chapter, lecture rather, with a few basic concepts, but now we want to go deep in this hypothesis testing, right? So here we want to do this. That last lecture we did 5 terminology which are associated with hypothesis testing. What is null hypothesis, what is alternative hypothesis, what is significance level, what is p-value, what is test statistic, and what are the two types of error, type 1 error and type 2 error. If you have not done that lecture, previous one, that is lecture number 21, then please do that. Otherwise you will find it difficult to follow this lecture. And if you do that thoroughly, then this lecture would look like a breeze. Okay, so practical examples of hypothesis testing, where this is used in data science and machine learning. It is used in many other aspects also, in business analytics and others, but we want to focus from our domain point of view. So one is in feature selection. So suppose I have one response variable. I am predicting the salary of my employee, and I am hiring a new employee, and based on certain traits, I am predicting the salary. Now there are so many traits: age, date of birth, then seniority, then qualification, then gender, then maybe past salary, then also many factors are there on which my predicted salary will depend. But the question is, do I need to build a model which will take all these features, or I can build a model by removing a few features and make a simpler model? Because we have seen that simpler model actually helps to avoid certain problems like overfitting, etc. Right? So for that we will use chi-square test for categorical variable. And what is that chi-square test? That we have not yet done, so that we are going to do. Similarly, other application of this is model comparison, right? Now in this model comparison, we can compare the performance of two machine learning models to see if one significantly outperforms the other. And these we will be doing in practically each and every problem that we are going to do in our next few chapters, right? Because whenever some data is given, that there is no one size fits all kind of rule in machine learning, that every time random forest will only give the best result, or every time XGBoost will only give the best result. On certain data sets, it is possible that simple decision tree might give better result. On certain data set, even simple linear regression might give better result. But on certain data set, it is possible that random forest gives better result. So on same data set, we will run multiple models, and we will compare the performance. And for that also, we will use hypothesis testing. A/B testing that we have already done. That suppose you do some different app layout, and that means suppose you are running one particular online application on Google Play, and you have decided that let us try some new user interface, right? But you want to play safe. So what you do is you keep the old user interface for some users and new user interface for only some few sample users. And then you measure certain KPIs. KPIs is the short form for key performance indicators. And this is a business terminology. So I'm including just because when you go to internship or somewhere, then you should not feel out of place, right? So if there is key performance indicators like this, then in that case, I can choose either my CTR, click-through rate, as my key performance indicator, and I will try first app layout, whether it gives better click-through rate, or second app layout, whether it gives proper CTR, and then whichever gives proper CTR, that will be, or higher CTR, that will be chosen layout, right? Okay. So again, hypothesis testing will be required. So null hypothesis in that case will be by trying a second app layout, there is no change in the CTR, click-through rate, right? So that is the null hypothesis. An alternative hypothesis will be, yes, when app layout is changed, then click-through rate significantly increases, improves, right? Now you have to test whether a null hypothesis is correct or alternative hypothesis is correct. Now sometimes click-through rate is difficult to estimate. So at that time you can take other KPI, other metrics, say, okay, click-through rate is not much changing by different layout, but maybe after changing the new user interface, the revenue of my app or the number of paid subscribers of my app, has that increased significantly, like that, okay? So that is how we do it. Now here we want to discuss about hypothesis testing. I said that this business problem is solved by making a null hypothesis and alternative hypothesis and then testing whether null is valid or whether alternative is valid hypothesis. But the question is how to test it. So there are multiple tests which are possible, which are called one sample test, two sample test, paired sample test, ANOVA. ANOVA is a short form for analysis, AN, of O, variance, VA. Okay, so first two letters of this, first letter of this, and first two letter of this. So that is how the name is made, analysis of variance, ANOVA. Chi-square test, correlation test, and Z test. So now we want to do a detailed discussion of all these 7 different tests one by one. Okay, so you must pay attention on these things. Now earlier, what was the way to introduce this test? Then earlier the way to introduce this test was actually taking the Z table or the T table, which are like our log tables which we used in earlier standards. So that kind of ready-made tables are available, and then we used to see the value actually manually like that. But obviously that way, even if it is taught that way, when you are asked to build something which will test the hypothesis, then you will not be able to do it visually and by using tables, right? So fortunately, Python has ready-made tests which you just have to import from scipy.stats library. For example, if you want to do one sample test, t-test, then t-test underscore one sample should be imported. If you want to do another, for example, two sample t-test, which is also called independent samples t-test. So as the word itself indicates, there are two independent samples, right? So it is a two sample t-test, and there at that time you will, from same library, scipy.stats, you will import t-test underscore ind. Okay. Similarly, if you want to do this paired t-test, then at that time you will use t-test underscore rel. Okay. Again, it is same library, scipy.stats. So that means our entire data science can be handled by a few libraries. NumPy, Pandas, Matplotlib, Seaborn. To make interactive plots, you may need Plotly. To do statistical calculation, you may need scipy.stats. And to then finally build the model and do the test, train, split, and bring the algorithm, random forest or XGBoost, etc., you will need scikit-learn. Around these 6 or 7 fundamental libraries, and almost 90% of the jobs in the data science or machine learning can be handled. So third part of the chapter, that will introduce the use of this scipy-stats. So for paired t-test, I will import t-test underscore rel, okay, relative. Then maybe here there is ANOVA, right? So for ANOVA, here we will import from scipy.stats, import f one way. ANOVA is also called, ANOVA is of two types, one-way ANOVA and two-way ANOVA. So we will import one-way ANOVA, okay. So then similarly, suppose I want to do chi-square test, then from scipy.stats, import chi2 underscore contingency. And maybe still one more test is I think left, that is correlation test. So for that I will import Pearson R, that is Pearson correlation, okay. And still I think one is left, that is no, that is just a practical application, but Z test was there, right? Yeah, for Z test, I think you will have to do things a little bit manually only, because there is no ready-made Z test available. Okay, so yes, you have to do a little bit manual coding, but that we will see whenever it comes. At present, we take the first test, that was one-way t-test, right? So let me find out that one sample t-test. Right, okay, one sample t-test. So these are the names of the 7 tests, and I told you that these first 6 can be directly imported from scipy.stats library. For this Z test, you have to do some little bit of manual coding, right? So let us do this one sample t-test. First, where it is used? It is used to compare the mean or proportion of a single sample to some known value or a population parameter. Now, what is the meaning? Let us take examples and things become clear. A factory claims that the average weight of a product is 1 kilogram and you collect a sample and wants to test if average weight is significantly different. Now, here, what is the situation? Suppose you are purchase officer for a large multinational retailer like say Walmart, and you are buying some particular product in maybe millions and millions of numbers over the year from that supplier. Now that supplier says that my product would be exactly 1 kg. Now if that product comes out to be less than 1 kg, grocery product or whatever, less than 1 kg in the packing, then in that case it is your reputation as a Walmart that is at stake, right? So if you are purchase manager, then you are assigned the responsibility that you have to ensure the quality control that each and every sample should be exactly 1 kg, right? Now there is a problem. Will you go and measure the weight of all millions of cartons which are coming from your supplier to the Walmart godown? Because if that is the only thing how it is being done, then what is the use of these statistics and this central limit theorem? I told you that that is not how things are done. The art of statistics or the art of central limit theorem or the art of this even hypothesis testing is you take multiple samples and find a certain parameter. In this case, I will find the weight of one carton. That is my parameter, right? From these different samples, and then what you do is find the mean weight, which is also called the true mean. That you know, that is the mean weight of each mean weight of multiple samples, right? And you will assume that under certain circumstances, that mean weight of multiple samples give a fair idea about the mean weight of entire population of millions of cartons which you are buying from that supplier. And how many samples are required? Hardly 50 to 100 samples are enough. Say 100 samples for safety. And how many cartons you will take in each sample? Minimum 30. So you are taking say 50 samples. Now why this is called one sample t-test? Because here you are comparing this mean or proportion of single sample to a known value or a population parameter. What is the known value here? Weight of the product is the known value, right? So you collect a sample and test if the weight is significantly different. Okay. Now suppose you make this kind of hypothesis. Normally null hypothesis always means everything is fine, status quo. So in null hypothesis you say that yes, the average weight of say 50 samples which I have taken is 1 kg. But the alternative hypothesis says that no, the average weight is not 1 kg, or maybe it is less than 1 kg, and therefore your reputation is at stake. So how will you test it? So one sample t-test is used. If population standard deviation is unknown, and it is most of the time unknown because population means those millions of cartons which you are buying from your supplier. So its standard deviation is mostly unknown. That is why this one sample t-test is always preferred. But sometimes population standard deviation is known in some other cases, not in this case, but some other cases. So at that time we can use, instead of one sample t-test, you can also use Z-test. So Z-test is our last point of discussion. Before that we will discuss all possible tests, and then at the end we will say about Z-test. When to use Z-test if the population standard deviation is known to you. But that is a rare case. Okay, sometimes it happens, however, and we will take a practical example also. But at least in this case, population standard deviation is not known to me, so I will have to use one sample t-test. This would be at that time my null hypothesis, and this would be at that time my alternative hypothesis. We will see how to test it, but let us take first another example. So a manufacturing company tells that average weight of their product is 500 gram. Again, suppose there is a company which supplies to your particular online platform, and it claims that our each carton has 500 gram weight. Now how do you find if they are not cheating you, or that means indirectly your customers? So then you can take sample of 30 products and find the average weight to be around 495 grams with a standard deviation of 5 grams. So you actually went there as a purchase officer and selected random 30 samples. Okay, not 30 samples, but rather each sample had 30 data points, and you found that average weight of this sample came out to be 5 grams, 495 grams with a standard deviation of 5 grams. That means it was either in the range 490 to 490 to 500. That is 495 plus or minus 5 grams, right? Now the question is, as a purchase officer, will you deem this as a significant deviation, and will you reject your supplier's samples, or whether you will say that okay, some difference is coming, that instead of 495 grams, sometimes 490 grams is coming, and sometimes 500 grams is coming, but it is not statistically significant difference, so we will accept the supplier's claim. Okay, now here hypothesis will be average weight is 500 grams because the company claims that average weight of his product is 500 grams. So that will become the null hypothesis. Null hypothesis means everything is fine. There is absolutely no issue with the claim. So it is things are as claimed. That is the meaning of null hypothesis. While average weight alternative hypothesis will be average weight is not 500 gram, or if you can also pick it that way, that it is less than 500 gram, right? So that is my alternative hypothesis. Now in that case also you can use one sample t-test. So what is the key to understand when to use one sample t-test? Whenever some number is given clearly that 1 kg is the sample or 500 gram is the sample, or the length of the rod which is being supplied for piston to my auto company, that will be exactly 69 or 70 centimeter. So that is a number now, right? So at that time you can use one sample t-test. Now we will do this second example, that is the company is claiming that the average weight is 500 gram, and you have taken 30 products from their company, and you are finding that the average weight is 495 gram with a standard deviation of 5 gram. So now whether you will call this a significance difference or not. If it is a significant difference, then you will say that null hypothesis is wrong. Okay, because null hypothesis says that it is 500 gram. But if the difference, see, the difference is there, that is very clear, because the minimum is 490 and the maximum is 500. So there is some difference. But if the difference is not much significant, then in that case you will say that null hypothesis is correct. But if the difference is significant, then in that case you will say that no, alternative hypothesis is correct, and therefore this sample must be rejected. Right? Before passing the bill, the purchaser will test this kind of things, and then only he will pay the supplier. Okay, so one sample t-test. Now, how to do that? So these are our well-known steps. The only new step is this, as I said, that you have to import this t-test underscore 1sem from scipy.stats library. Now generate synthetic sample data. So this is the seed sample weights I am generating. So that is random.normal, log, that is the mean value, and scale, that is the standard deviation value, and size is equal to 30. So you are generating 30 products. The mean is 495 gram, and the standard deviation is 5 grams as the real situation is there, because I cannot take you to some actual supplier and where we will be measuring the weights by using some weighing scale. So I have to simulate that situation using a code, right? Now population mean, that is the weight claimed by the manufacturing company, is 500. Now you are performing one sample t-test. So how to do? Find t-test and p-value, and is equal to, always see the right side first, and then the value or the result of the right side, they will be assigned to the left side, right? So this t-test underscore one sample, that actually does not give just one result, but that gives two results. And first result will be assigned to t statistic, and second result will be assigned to p value. Okay, fine. Now, okay, this gives two results, but the question is what parameters I have to supply to get those results. Then one is the sample weights. Sample weights I have generated here, that 30 observations I have generated, right, with mean of this much and standard deviation of this much. And another is the population mean. So I am generating, I am knowing the value. That is why I am using the one sample t-test. So this parameter is known to me, and these sample weights are also known to me. I am knowing entire data set of 30 observations with mean is this much and standard deviation is this much, right? So then display the test result. Now what I can do here is I can take this much in a new cell, and similarly this much also in the new cell after that cell. Okay, just for the clarity of understanding. So here what we are doing is just this visualization also we have shifted, right? No, I think there are multiple visualization, 4.2, 4.3, just a minute. So yeah, 4.1, 4.2, 4.3. I have just shifted display the test result. 4.3 is shifted, but this is 4.1, and still I have to shift 4.2. Okay, so 4.2. It is better to keep different things in different cells initially, because otherwise when I execute the cell, you will be bombarded with a big amount of information, right? And then you will not be able to follow. So let me even just print this t stat which is obtained in the previous t underscore test stat, and in second line I will print the p underscore value. Okay, rest of the steps I have already explained. So up to this I have already explained. Now if I do that, then I get the t stat is minus this much, and this p value is coming out to be very small, because it is 5.8182 into 10 raised to minus 8. So that is actually somewhat like this, that 0.0000000. So that is 7 zeros and 582. That is my p value, right? So p value comes out to be this much, while t stat comes out to be large value. Forget about the sign, but about the t stat you have to see, if it is large, then you have to note down that t stat is pretty large. Now that pretty large is a relative thing. So large with respect to what? That is why we don't rely on t stat for hypothesis conclusion, but we rely on p value only, because for p value we know that there is some significance decided, alpha, and yesterday we had said that thing, that alpha is equal to 0.05 So these are the core concept in which this significance level. So 0.05 or 5%, that is the significance level. And if the probability, that is the p-value, comes out to be less than 0.05, then we reject the null hypothesis. So that is means that p-value helps us to decide whether null hypothesis is to be rejected or not, right? Not t-statistic. But t-statistic gives an idea that if t-statistic is large, then usually you can be sure that the p-value is going to be less than 0.05 or alpha, right? So here I am writing, just for the sake of record, that we are taking alpha equals 0.05, right? So this p-value is very less than alpha, so that means null hypothesis can be rejected. And what was my null hypothesis? That the average weight is indeed 500 grams as claimed by the manufacturer. But that must be rejected. That means average weight is not 500 grams, and therefore the difference is statistically significant. Okay, so then you have to take that supplier to some task, right? Here we are printing the same result and printing the result, hypothesis acceptance or rejection result, right? So these are p statistic and p value. It is so small. Here when I printed out, I got this. Okay, so it is so small that when you round it off, it came out to be 0 only. So that is also fine. That means it is less than alpha. And if p-value less than alpha, then reject the null hypothesis. So here I am getting reject the null hypothesis, and therefore average weight is significantly different from 500 grams. So don't say that manufacturer. He is not accurately packaging his supply, right? Now let us try to do the same thing by visualization. Now, normally this p-value itself is considered the conclusive thing. If p-value said that reject the null hypothesis, that means final. But sometimes visualization also helps to get a further confirmation. So we plot a histogram of this sample weight. What are sample weight? We took 30 samples from the supplier whose mean was 495 gram and whose standard deviation was 5 gram. So let us take that data set of 30 sample weights and let us plot histogram with KDE plot. Okay, that will give some information. Then we will plot some box plot also, and then we will plot box plot of sample weight, and then difference between sample mean and population mean. Population mean was 500 gram because the supplier manufacturer claimed that my this weight of my product is 500 gram. So that is comes population mean. So we will plot some graphs and see if they are significantly different. So that is just an additional confirmation that whatever value you got from the p-value, that the null hypothesis is invalid here, and average weight is significantly different from the 500 gram value. So let us see if visually also it gives the confirmation. Now here if you see very first graph, that is the histogram, then that shows the red colored line, that is the population mean. Okay, 500 exactly, while the green colored line, that is the sample mean, that is the true mean, okay, or the mean of all sample weight, okay, and that comes out to be far different. You can see the difference is quite more. It is more than 495 is here, right? So that means this is somewhere I think 493 or something, but the mean of the all 30 samples came out to be less than 493. So it is not allowed. Same way box plot for the 30 samples which you took from that supplier. Again, this is the population mean or the weight which is claimed by your supplier, but this is the sample mean somewhere 493 gram or somewhere. So that means that your sample mean is significantly different, right? Now difference between sample mean and population mean is what you are plotting in the third plot. Third plot is here, difference between sample mean and population mean, right? So the dotted line shows that there is no difference, but here you can see that there is significant weight difference. Otherwise, so -6, okay. So that means that weight difference is not negligible in that case, okay. So up to a certain limit you could have allowed it, but the difference is significantly higher, and therefore you will say that the supplier is perhaps either trying to cheat you or he is not careful with his packaging. But in either case, it will be harmful for the reputation of your online selling platform, and therefore you will reject that supplier's bill and you will tell him to resupply the product, entire batch of product, and be careful from next time, right? So this is the explanation of the visualization which I have already done. So next, a red dash line at 0, the last graph requires some explanation, indicates no difference, but you did not get the red dash line here. In fact, you got your red dash line somewhere at this point here, okay. So that means that if it would have this whole purple color rectangle that would be of 0 length or just maybe this much of length, then you can say that okay, there is not much difference, but this is a significant difference, so you have to take your supplier at task. So that was the discussion about one sample t-test. Next we will discuss about two sample t-test here. That will be next lecture. Thank you and stay tuned.